Alrighty, in this lesson, we're going to be talking about 5.3, the binomial distribution. So this is our third objective. We're going to find the exact probability for a certain event happening X for successes in how many trials for a binomial experiment. Some variables can have only two out. So some variables can have only two outcomes, or the outcome can be classified in exactly two categories. For example, when a coin is tossed, it will either land on heads or tails. In addition, a multiple choice question with five options would have one correct choice and the other four choices would be incorrect. Thus, the answers choices be classified as either correct or incorrect. For it to be a binomial distribution, guys, it's got to have only two options. It can have multiple options, but only two things can happen. It is either a success or it is a failure. So even though you can flip a coin heads or tails, it's either heads or not heads. For a five multiple choice question, it's either correct or it's not correct. Now, there could be multiple not corrects, but again, only two outcomes can happen. It's either going to be correct or it's not going to be correct. These situations, again, are called binomial distributions, or I guess in this sense, binomial experiments, meaning only two outcomes can happen. Each repetition of the experiment is called a trial. So each time you do it, it's a trial. So in a binomial experiment, is a probability experiment that satisfies the following four requirements. There must be a fixed number of trials, meaning you have 5 events, 10 events, 22 events, but there is a fixed number of trials that's going to happen. Each trial can only have two outcomes, or outcomes that can be reduced to two categories. So again, in a multiple choice question, you might be going, well, you have a probability that it be an A, B, C, D, or E, but it can come down to out of those five options, either A is correct or not correct. B is either correct or not correct. So that's what basically what I'm trying to say there. So these outcomes can be considered either a success or a failure. The outcomes of each trial must be independent of another. One cannot depend on the other. So meaning if I wanted to know the probability of drawing a diamond out of a deck of cards, then I would be looking for the probability that it's a diamond or it's not a diamond. But if I pull a card out and I don't replace it, I'm now affecting what the next one outcome is going to be. It has to be independent of another. So if I do with the card, I have to put the card back. And then the fourth one, the probability of success must remain the same for each trial. So this can't just be the more times I do it, the more likelihood that I be successful. It has to be the same. It has to be the same likelihood each time an event happens. All right. So those are the four requirements for a binomial experiment. So a success in a binomial experiment is neither good nor bad. A success means that the result was what the researcher was looking for. For example, a multiple choice test is given and the outcomes are either correct or incorrect. If the researcher is looking for the probability of incorrect answers, then an incorrect answer would be considered a success. On the other hand, if the researchers were looking for the probability of correct answers, then a correct answer would be considered a success. All right, so let's look at example 11 here. We're going to classify each one of these as if it is a binomial or not. All right, so when I first look at these, it says roll a standard die 200 times. All right, this situation is not going to be a binomial because it did not specify, am I looking for it landing on 1 or not 1? So this is not a binomial. There is 6 outcomes here. I needed to get it down to 2. So again, I could say rolling a standard die 200 times to see how many times it lands on 1. Then I could go, all right, it's either 1 or not 1. If it would have said that, I could have then said binomial. B says, survey of 100 shoppers asking for their favorite exercise shoe brand. Again, this is not a binomial. There is too many outcomes out there. The survey would have to change it by saying the survey 100 shoppers asking if their favorite exercise shoes brand is Nike or not Nike. That would be the outcome. All right, so again, these broad ones can be limited down to 2 options, but the the researcher here has to say that. Part C, a survey of 100 teenagers asking if they played the video game Halo. This is a binomial experiment because it's 2 answers. They've either yes, played the game Halo, or no, they have not played the game Halo. Part D, we're going to ask 300 viewers if they recall seeing a Coca-Cola commercial during a particular show. Again, this would be a binomial because they either A, saw it, or B, did not see it. So this would be a binomial experiment. And then part E, test 4 brands of aspirin to see which brands are effective. This is not a binomial. Again, you can only have 2 outcomes. Now, it doesn't have to be like yes or no, but it could be just 2 brands of aspirin. Is aspirin A successful, or is aspirin B successful? And we can still get it down. If the researcher wants aspirin A to be successful, then what's the likelihood that aspirin A works and where aspirin B does not work, or any of those outcomes? But again, only 2 choices can be made. All right. And again, it gave you some spots there for the solution. Here it says the outcome of a binomial experiment and the corresponding probabilities of these outcomes are called a binomial distribution. So notation used for binomial experiment. N will still represent the number of trials. X will be the number of success in trials. So if X is a counting number, it's 0, 1, 2, 3, maybe 4 out of the so many N trials. P of S, that would just stand the probability of success. P of F will be the probability of failure. P will represent the numerical probability of the success, and then Q would represent the numerical probability of failure. Now we can calculate pretty easy by just taking 1 minus the probability of success. Going back to that 5-question multiple choice, and if I wanted to count the probability of getting the correct answer, then my probability of success would be 0.2, and my probability of failure would be 0.8. All right, and I could easily do that by doing 1 minus 0.8 versus having to do 1/5 plus 1/5 plus 1/5 plus 1/5 to get the 0.8. All right. So let's go a little bit further into this. So a binomial probability formula. So in a binomial experiment, the probability of exactly X successes in N trials can be calculated using our permutation and combination type of formulas with a little bit more. So using our combination times a little bit more, we can produce an equation. So you can either use the combination, which again, you would take your N trials divided by N minus how many success trials you would have, or exactly, let's say you take 30 question tests. You want to know what is the probability that you'll get exactly 21, because you've calculated that would give you a 71 or whatever you get on a test, right? And you're like, all right, what's the likelihood or the probability that I get exactly 21? So your N would then be 30. then you would have n minus 21 because your x would be 21. X again represents how many successes in the trials that you plan on having. And so therefore you would have the probability of success raised to 21 times the probability of failure raised to the ninth power, because that would be 30 minus 21. And then you just do the math. And again, this right here, again, just represents the combination equation. These are all the same. So this represents this, and then they kind of just rewrite it for you here. But this comes from the previous chapter. So keep in mind that no successes would mean that x equals 0 and must be considered, right? So if I want no successes, that can have a probability outcome as well. And then, of course, as always, a lot of this stuff can be calculated using technology. Once we know which each number need to go into each variable, we can just plug it into our calculator to get the outcome. I definitely don't expect you to do this by hand in any way. That'd be pretty difficult. So let's look at example 12 here. There you go. Probability of rolling twos. So a six-sided die is tossed 5 times, right? So there is our n. A success is tossing a 2. A failure is tossing a result that is not 2. Each toss of the die is independent from one another. So the probability of getting a 2 is a 1 out of 6 chance. Probability of not getting a 2 will be a 5 out of 6 chance. We want to find the probability of getting exactly 3 2s. Right. So what we're going to do is we're actually going to fill out this. Actually, I think they filled it out for you. Just kind of looking at the math here. So we considered all these possibilities right here. There we go. So the probability of exactly 0 2s in 5 rounds is 0.4. That's almost a 40% chance that you will not get a 2 at all. There's actually a 0.40% chance, sorry, a 40% chance that you would get exactly 1 2. There's a 16% chance that you would get exactly 2 2s. There's a 3% chance that you would get exactly 3 2s. There's a 0.3% chance that you would get exactly 4 2s. And that looks to be like a 0.01% chance of getting exactly 5 2s. All right, so they kind of did all the math. They just plugged it in and they calculated it. But we can use that to help us answer these questions. Let's see. Okay, I want to do it without them doing it. So, but you can see the whole process. So I'm going to do A here. Part A says find the probability of getting exactly 3 2s. By doing that, oh man, hold on. There you go. All right, to get exactly 3 2s, they did it for us right there. To get exactly 3, the answer there is just simply going to be 0.0322. So when doing exact, it's super easy because that's all you have to do. It gets a little different when it says find the probability of at least 3 2s. So that means I get 3 2s or more. So now I got to do 0.0322 plus the probability of getting 4 of them, so 0.0032 plus 0.0001. And when I do that, it actually comes out to 0.0355. So I now have a 3.55% chance of getting at least a 3. Then part C now says find the probability of at most 2. So that's going to be 2 being like the max, so at most 2. So it's going to be that number or least or less. So I start with 0.1608 plus 0.4019 plus 0.4019, and that comes out to 0.9645. So I have a 96.45% chance of it having at most 2. That means 2 or less. All right. And again, they do all the calculations for you, but I wanted to do it with you as well. All right, let's look at example 13. They don't do the math on this one. All right, so there you go. They break it down with more of the formulas, but once you have all of those, you're good to go. And really and truly, just type them in the calculator, get the outcomes, and then just be ready to answer all the questions that go with it. Oh, dang. Trying to get it directly on it is like almost impossible. There you go. So example 13, probability of too much concern. In a survey, 3 of 4 students said that the courts show too much concern for criminals. Find the probability that at most 3 out of 7 randomly selected students will agree with this statement. All right, so here's that issue. At most 3 out of 7. So we have to find the probability of 3, 2, 1, and none. All right. So I'm actually going to switch to my calculator to kind of show you that. All right. So what I'm going to do here is I'm going to first do the probability of 3. So what that's going to do is I'll do control divide. That'll give me that fraction to do my combination. So that's going to be 7 factorial. And the factorials are located by the G over. We're going to put parentheses here. And this is going to be 7 minus at most 3, correct? So that would be 7 minus 3 first, factorial. And then times 2x factorial. So that'd be 3 factorial. All right, there's my combination. And I'm going to multiply that by my probability of success. So my probability of success, again, find the probability that 3 out of 7 randomly selected students will agree with this statement. Well, the first statement was 3 out of 4. So that means I have 0.75% chance of success. And I want that to happen 3 times. Times the probability of failure. That's going to be 0.25 raised to the 7 minus 3, which is 4. All right, that's the first one. And what I'll do with that is I'll do this. That will give me at most, that will give me 3. And then I'm going to hit enter to copy it, or I'll scroll up to it, hit enter. And I'm just going to change these to 2, because at most 3 was the most. So that's 2. This will now be a 2. And this will become a 5. I'll hit enter, and then I'll do it again. This time I'll do it with 1. And this is probably, in my opinion, the quickest way to get the calculations. And we'll do it one more time. This time that 0 of them will agree with me. I know it doesn't make any sense to put those zeros there because it's just going to be that. But just for sake of argument. All right, now, best way to do this. We're going to go up to the first one, which was this one. And we're going to say this plus this answer here, plus that answer there, plus that answer there. And we get this as our outcome. So save yourself some time. Let's scroll back to the other side. All right, so again, this was the P3 plus P2 plus P1 plus P0. And again, we're looking at finding at most 3, so 3 or less. And that came out to 0.071. So basically a 7% chance that you'll get at most 3 that will agree with you. All right. So there's an example with that. All right, this next part here, You're given a table. Definitely going to want your table from your back of your book when doing the rest of these tests. Um, I did make the test where the formula charts will also be provided for you as well, so you can pull it up when you think you need it. Um, but these are going to be very important. This first one that we'll look at is just the binomial distribution. So you have N there being the sample trials, X just being how many do you want to be successful, and then the probability of success is written there from 0.05 to 0.95. Obviously, if it's not something that can be done within 7 trials, then you can't use this chart and you would go back to the formula at hand. Right? But let's do one saying that it is. So this one says a probability of wanting a toy. So if 20% of children were reported to want a particular toy, let's use the table to find the probability that exactly 4 of 7 children want the toy. So I'm going to go back to the table. So here's the table. So I have, let's see, so 20% probability success. So I'm going to be looking at this column right here at 0.2. Or reported to want a particular toy to find the table. Exactly 4 out of 7. So that means I have 7 in my trial. So here's 7. And I want exactly 4. But 0.2 was the third column. So here's 7 trial. I want exactly 4 at a, there you go, at a 20% chance. So there is my probability right there. I already have my answer. So the answer here would be 0.029 for your A. So that's what you'd write, and then you're done. Right? Using the chart to help you get the answer. All right, the next one says at most 3. So at 7. So I still got 7 kids. This time I want at most 3. So that's going to be 3 or less. So this time I would want to add all of these numbers up. So for part B, I would do 0.210 plus 0.367 plus 0.275 plus 0.115. And when you do that, it actually comes out to 0.967. So if we want at most 3 of the 7 children want this toy, we have a 96.7% chance of that happening. Part C, at least 4. So that means 4 or more. So that means this time I would add up these two numbers. Now, you might be asking, why are these numbers not here? It's because it's so small of a number that it's just 0. The probability that 6 out of 7 kids at a 20% success, it won't happen. That's how small that number is. So for part C, I really just got to go 0.029 plus 0.004. You can add 0 if you want, but it's all going to come out to being 0.033. So there is a 3.3% chance that you at least get 4 or more children that want that toy. Right? So that's how you can utilize the table to help answer your questions. Again, the table is only useful up to 7, unless that's only part of it. It might keep going. If it does, you can use it as much as you want. All right. So in example 14, we just did that. So let's look at our fourth objective. We're going to find the mean variance and standard deviation for the variable of a binomial distribution. The mean variance and standard deviation for a binomial variable can be found using the methods for any probability distribution, but there are shorter mathematically equivalent formulas for the mean variance and standard deviation for binomial distribution. Since there's only 2 outcomes that can happen for a binomial distribution, we can get the answer a lot quicker. So for instance, to find the mean of a binomial distribution, all I got to do is take the number of trials times the probability of success, and I got my answer. For variance, I take that mean and I multiply it by the probability of failure, which is 1 minus the p, and that would give me the variance. And then, of course, if I just take the square root of that result, it would then give me the standard deviation. Right? So a lot quicker of a way to do this if I know I'm dealing with a binomial distribution, and I know I'm dealing with binomial distribution if there can only be two outcomes for each trial given. So again, these formulas are especially helpful when for a binomial experiment, the number of trials is very large. So let's look at this example 15 here. It says for a binomial distribution, so I know it is, for which there are 500 trials. Now, I don't want to have to do the math for 500. And the probability of success is 0.25. What is the mean, variance, and standard deviation? So since you are told it is a binomial distribution, you are given your n and you're given your probability of success. The mean, remember, is n times p. So for this guy, this will be 500 times 0.25, which comes out to 125. So the mean average would be 125 successes in that 500 trials. So basically what that means is if I did 500 trials for something, you did 500 trials for something, someone else did 500 trials, and we did a whole bunch of those, on average with all of us, we should have about 125 successes in our 500 trials. Now for variance, you would then take that mean of 125 and multiply it to your failure. So that would be 0.75 in this situation, which comes out to 93.75. So there's your variance. Remember, that's your basically how variety of outcomes you can get. And then if you just take the square root of your variance, it comes out to about 9.682. So give or take 10 successes would give or take the standard deviation from the mean. Right? So now let's look at example 16. So in example 16, mean and standard deviation of number purchasing internet services. 32% of adult internet users have purchased products or services online for a random sample of 200 adult internet users. We're going to find the mean of standard deviation for the number who have purchased good or services online. So again, there's a 32% of adult internet users have purchased a product or service online. So it's either they have or they have not, and 32% have. For a random sample of 200, so this is probably a success. This would be my N, 200 adult users. We want to find the mean standard deviation for the number who have purchased goods or services. Now, if we were looking for who have not, this P would then turn to a Q, and then we just calculate our P. All right. So is this a binomial experiment with 200 trials and a probability of success of 32? The answer is yes. They either did purchase it or they did not. So bam, done. There are a fixed number of trials. There's 200 people in this trial. Each trial has two outcomes. This is true. They either purchased or did not purchase these internet services. Each trial is independent. So if I use internet services, that's not going to affect the next guy who is going to be using internet services. All right. After that, so let me scroll down, get the rest of it. All right, there we go. I'll just scroll down and get that last one. All right, the probability of success remains the same for each trial. Again, this is a yes. 32% of them use it. So we have our probability of success change. It does not change. The mean number of adult internet users out of 200 who have purchased product or services, again, for the mean would be the number of trials times the probability of success. So 200 times 0.32 is 64. So again, if I survey 200, you survey 200, someone else surveys 200, on average, we should see that 64 people use online services out of 200. And then the standard deviation of adult internet users out of 200 who purchase these products. Remember, to do the standard deviation is going to be the square root of the mean. So that's 64 times the probability of failure. So that would be zero point 0.1 or 1 minus 0.32, which comes out to 0.68. And that comes out to be about 6 points. We'll go 3 decimals, so 597. All right, so our standard deviation, about 65% of our data, again, should come out 6.5 plus or minus people saying yes, they use internet services. All right, so again, knowing that's binomial distribution, there was only 2 outcomes. We were able to quickly get the mean, standard deviation. If we wanted the variance, we would just square that number and we would have our variance as well. All right, just a couple more examples, and that should be good for you for your homework. All right, so in example 17, mean and standard deviation of the number of students. So in a sample of 3 or 4 students said they purchased the products or services online. This time we want to find the mean and standard deviation of the number of students who say they have purchased products or services online of 7 randomly selected students. So we did this earlier, but this time we're now going to calculate their mean. So again, the mean is N times P. All right, so there is 7 randomly selected students. Probability of success is 0.75. So in this case, that would be 7 times 0.75, and that comes out to be about 5.25. So on average, we should get 5.25 students saying that they do purchase products or services online. Well, this is not quite the same, is it? This was about a toy earlier, I think. Maybe it wasn't. I can't remember how. Anyways, all right, then standard deviation is the next thing we were asked to find. So remember, that's the square root of N times P times Q. All right, so we already got the N times P for the mean, so that's 5.25. So we're just going to multiply that to our failure, so that's going to be 0.25. And when we do that, we come out to 1 point, we'll go to 3 decimals, so 146. All right, so that's pretty good there. Hopefully not too many questions. Let's do one more just in case there are. All right, so in this one, in a survey, 20% of the children were reported to want a particular toy. 7 children, what is the mean of standard deviation of the number of children? So this is a binomial distribution. They either wanted the toy or not want the toy. Probability of success of wanting the toy is 0.2. And then there were 7 children chosen. So there's my sample. And so then to find the mean, I would again N times P. In this case, that's 7 times 0.2, which is 1.4. So 1 and almost a half of a kid would want a toy on average. To find the standard deviation, remember that's the square root of N times P times Q. I already did N and P, so that's going to be 1.4 times my Q, which is 0.8. So that comes out to 1 point, and there's 2 decimals here technically, so I'll go to 3. So that's going to be 1.058 for my standard deviation. All right? And you simply just type them in the calculator. That's all I did. All right. Hopefully that's everything you need to know for chapter 5. If you feel like you need more examples or you want something seen in Excel, I don't have an 84, but I can definitely help you with Inspire. And I can probably work through an 84 if you need some help with that. But if you have no other questions, I'm going to go ahead and move on to chapter 6 in the next lesson. See you in the next video.